Yes, hello students, Ross Technology Pulukwani. As we are upgrading tomorrow, let us go through this paper, which we are upgrading. Tomorrow is Friday, the 7th of November, and the 2025. So we are upgrading paper 1 physics. Let us explain this together. As we do so, where you don't understand, you can inbox me on 0785 222041, November 2024, physics paper 1. All right, now the question says here that 1.1, the several forces are acting on a moving object, okay? Several forces on a moving object. Which one of the following statements is correct when these forces are in equilibrium? When they are what? In equilibrium. Okay. Now, Newton's first law of motion says that a body will continue to remain at rest altogether, all continue moving with a constant velocity in a straight line unless an external force is acting on it. Okay, so also constant what? Constant velocity. Okay, so now at rest, that's why we have got our F net. Okay, F net equals to ma, and in this case, because it's at rest, so it has zero acceleration. It's not moving, so that is zero. It's also at equilibrium. And then a constant velocity. In this case, because the forward force is balanced by the backward force, we are going to move at a constant velocity. In that case also, because of the constant velocity, also acceleration will be zero, and hence also it's going to be at equilibrium. So in here, they say velocity has got what? Increasing velocity. That's not correct because it is what? It is accelerating. It won't give us zero. Then the object is moving at a constant velocity, okay, and the kinetic kind of object is decreasing. That's not right. The object has a non-zero acceleration, okay, but the best answer here would be moving at a constant velocity. At a constant velocity, because in that case we are going to be here. Newton's first law of motion, whereby the forward pulling force is balanced by what? By the opposing force of friction. Okay, so the answer is what? Is B. In this case, that is moving at a constant velocity. It's going to be at equilibrium as well. Okay, 1.2 here. A stone thrown vertically downwards from a top of a building takes 10 seconds to strike the ground. Consider the acceleration time graph below for the motion of the stone. The effects of friction are ignored. Okay, this acceleration here, this is time here. They say, what does the shaded area between 0 and t seconds shown the graph represent? Now, our area, now acceleration, as you can see here, is measured in what? In meters per second squared. Okay, altogether. What about time? In seconds. Okay. Now, our area, this one is a rectangle. We have the length, okay, times breadth. So our breadth here is the meters per second squared. If I multiply meters per second squared times the seconds here, as you can see, I'm getting what? I'm getting meters per second, okay? Because this is minus 2 plus 1, which is minus 1 here. And then this meters per second is for measuring velocity. But because now this velocity is over a period of time, and because of that, my answer here would be, they said part A, find the velocity of the stone. That's not correct. And then they say change in position. That's not correct because that would be what? That would be displacement. And then they say the constant velocity is of the stone. That's not correct as well because it is accelerating and it's not zero. It's 9.8. But the answer is going to be what? The change. The change in velocity. The change in what? In velocity. That will give us our what? The shaded area in this particular case. So our answer is going to be D here. Note that this is meters per second squared on the y-axis. This is seconds here. When you multiply them, you get this meters per second for measuring what? Velocity. But because it is done over a period of time and the body is changing position, okay, so it is a change in velocity. Okay, all right, let us continue. By the way, If this was velocity here altogether, and then time here, then the area would give us displacement. But now this was changing what velocity because here we have acceleration and then time on the x-axis. Okay, then next question here. They said that a ball moving horizontally has a constant momentum p and a kinetic energy k. The ball collides with a wall and bounces back horizontally. Immediately after the collision, the ball has a momentum half p. The mass of the ball remains constant. So the mass of the ball remains constant. So how do you find the kinetic energy? Kinetic energy is given by half times mass times velocity squared. What about the momentum? Now the momentum is mass times velocity, which I think you know very well. Now they say here that after collision, this one here, when it's going back, after collision, it's a half p. So if you've got a half the momentum, now because the mass remains constant, like in this case, it means the mass does not change. So because of this decrease of half, it means that the velocity must have decreased now. Maybe we lost some velocity because of hitting the wall. In other words, it's not the elastic collision. Okay, so it means this velocity here decreased here by what? By 2, by a half. Okay, so that's why it's v over 2 now. Because if you check here, to get a half p, this one I can write it as what? As a half, ne? Then a half what? A half mass times velocity, which that's what you see here as the half what? As the half p. Okay, this one here is it comes from here. Okay, and then we talk about now kinetic energy. Now this kinetic energy, like you see it here, here we have mv, so it's going to be now kinetic energy, okay, equals to a half, okay, a half what? A half m v squared, ne? No matter what is our v, it is v over 2 here, okay. Now this is the kinetic energy final, ne? Okay. So here must square this, okay. So when I square this, I'm gonna get 1 over 2 here, and then times mass times what? Times v squared um divided by 4, divided by 4, divided by 4, okay. Now a particular case, this a quarter, I can take it out like this, okay. I can say this is gonna be a quarter, okay, into a quarter into open bracket here, a half, okay, then the mass, and then v squared, which you guys can see that was our first k here because it's a half mv squared. In particular case, the final kinetic energy, okay, after the collision is gonna be a quarter times this one. But what is this? That's our k from here, so it's gonna be a quarter k, and because of that, our best answer is gonna be A. So the answer is A in this case. 1.4, 1.4. A force F acts on a box as the box moves from the rest down a rough incline at a constant acceleration. Now they say a constant acceleration, not constant velocity altogether. The force is up is parallel to the incline, okay, as shown the diagram below. So now they say the box moves from resting, and where is it going? Down. It's going down the rough inclined plane. Now because it's going down and the applied force is pulling up, now some learners, because they see the force going up, they're going to think that the box is going down. Read the question. They are saying I mean they're going to think that the box is going up. Ne? Read the question. They are saying that it's going down, 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 down. Okay. Then they say that the force is parallel to the incline as shown in the diagram below. Now they say choose the option that correctly incompletes the following statement. The work done by the gravitational force, in this case, is going to be our FG parallel taking this, okay? FG parallel, how together? Is dash the work done by the frictional force and the work done by the force. So if the box is going up, down here, then frictional force is opposing, isn't it? Frictional force is opposite. So it's our FK, okay? And because it's accelerating, like they said here, they said accelerating, isn't it? So in that particular case, this one must be bigger than these two combined. And so the work done by the gravitational force, okay, by gravitational force is going to be, they said here, equal to the sum. That's not correct because it's accelerating. Less than the sum, that's not correct because the body is going down. Then greater than the sum of. Now this would be the best answer because it is accelerating. Okay, are we together? Before they said equal the difference between, now that's not also correct because there will be zero. So now, but the body is accelerating down. So FG parallel is pulling it with a greater magnitude than the force F and the frictional force, and that's why it is accelerating. So the answer is C here. Okay, next here we have 1.5. They say here that a ball falling vertically downwards from point A strikes the ground with velocity v and bounces, reaching a maximum height at point B, okay, as shown in the diagram below. Which one of the combinations below is correct for the direction of the impulse of the ball upon striking the ground? They're saying which one is correct for the direction of what? Of the impulse on the ball upon striking the ground. Now we're talking about the effect of the impact direction of the impulse on the ball, not impulse on the ground, but impulse on the ball upon striking the ground and the magnitude of the velocity with which the ball leaves the ground. Now, first of all, because the first height is bigger than the second height, it means the collision is not elastic, meaning we are losing some energy and so losing some velocity altogether in the form of sound and so on, and heat. So because of that, um, the velocity, the velocity must decrease as we leave the ground. Okay, we are losing some velocity. Okay, so in this particular case, we want the direction of the impulse on the ball. Now, who is exerting impulse on the ball is the ground. And because the ball now moves upwards, that impulse must be upwards. So we're going to choose from this one or this one here. And then they're saying that the velocity with which the ball leaves the ground. So because of not having the same height here, velocity cannot be the same, but instead it's going to be less than. So we take this one here. Okay, so the answer is going to be C. The answer is C, 1.5. The answer is C. Are we together? Let us continue here. 1.6. The absorption spectrum of an element surrounding a moving star is observed on Earth and found to be redshifted. Which one of the following combination is correct for the movement of the star and the frequency of the observed light on Earth? I repeat, the absorption spectrum of an element surrounding a moving star is observed on Earth and to be redshifted. Which one of the following combinations is correct for the movement of the star and frequency of the observed light on Earth? Now, from our theory, because it's found to be redshifted, on the spectrum, the red end is towards where we have the lower frequency. And from Doppler effect, when we observe a decrease in the frequency, it means that the object was moving away. Are we together? I repeat, if the frequency of the listener is lower than the frequency of the source, then that source is moving away. And so because of that now, it means that we're going to choose from here, whereby saying away from the earth. So we choose either this one or this one here. But then, like we said, there is what? A decrease in the frequency. So that's not correct here. So I don't take it on here. So the answer becomes A. Are we together? Answer becomes A. Why? The red shifted means that what is observed has got a lower frequency because of the spectrum. The red end is towards the one with a lower frequency. And then from Doppler effect, if we compare the two, if the frequency of the listener is lower than that of the source, then something is moving away. In this case, it's going to be now away from the earth with a decreased frequency. Next question here, they say here that two small identical spheres, each with a mass m and a charge positive q, are placed in a vertical cylinder. The spheres remain stationary when their centers are r meters apart, as shown in the diagram below. Ignore all effects here. Now, this is a positively charged sphere and a positive charged sphere here. So we know that because they are all positive, we have a force of repulsion. And because this one cannot go into the ground, it's going to push this one. And this one, being a sphere with a mass m, there is the force of gravity or the weight acting on it is acting downwards. In other words, here, they're saying that which one of the following expressions can be used to correctly calculate the distance r? Now, because the sphere remains stationary, they say the spheres remain what? Stationary. Meaning here, this sphere here, this one, if I may draw the Fribo diagram, I'm gonna be having the electrostatic force, okay, all together, and then gravitational force, and because it is stationary, then the two must balance. Now to get my R here, they're saying which one should I use here? Okay, so now because of stationary, mean that the force of gravity, okay, equal to the force electrostatic, okay. And how do you find force of gravity? It's mass times the gravitational force, acceleration, sorry. And then what about this Fe? We use K times sphere 1 times sphere 2, the charges, divided by what? Distance squared, okay, from the centers, which is R in this case. And so we're gonna say that our mg, okay, because they said identical spheres and they're all positive, have the same charge q, so it's gonna be, we're going to say that in this case our q1 the same as q2, which you can call q. So you're gonna say mg equals to k then times q squared, okay, divided by r squared. So because I'm looking for r, I'm gonna bring it here. So my r squared here is gonna be given by k q squared divided by mg. And so from here, if I do square root, I can get my r, get my r here. So my r is going to be given by root of what? Of k q squared divided by mg. Okay, and so it is A to give us the r that we are looking for in this particular case. Okay, let us move on here. The kilowatt hour is a unit of, okay, now kilowatt hour, let us go to the basics. Because of this word wait here, we're talking about power. We know that power is the rate at which work is done. In other words, power is work done W divided by change in time. Okay, and because of this way, the hour is the concept of time, so we're going to multiply power times time to give us this W, which is work done. Are we together? And then now the work done is measured in joules together with the energy. Also, energy is measured in what? Also joules together. In other words, the work done, we call it energy. We call it what? Energy, electrical energy. And then, because this is a kilo and a kilowatt, now because this one here, it is in hours here, it means that this one here, they say kilowatts, okay? The kilowatts is for the power, then times hour, okay? So in other words, this E is our electrical energy. Is our what? Electrical energy. So don't note that it's not current, it's not power, but is what? Electrical energy. measured in kilowatt hours. All right. So that unit is for measuring what? Kilowatt hours. So that's what we have there. 1.9, they say here that the diagram below shows a simplified electric motor. The rotation of the coil is observed from the battery. Okay. Which one of the following statements is correct with the coil while the coil is in operation? The coil and the dash. Okay. Now they're saying that from the battery, the rotation of the coil, but by the what's a motor? Electric motor. Now, electric motor is a device which converts from electrical energy to mechanical energy. And this motor, we use what we call as the left-hand Fleming's rule. Ne? So now I'm holding my left hand here, and because the thing from the battery, this is positive. Ne? So current flows like this now, and like this. Ne? Okay. So as it goes like this is north here, and then note that when you want to get our direction here, the thumb, I mean the first finger of the left hand must be pointed how? From north to south, ne? This one here, northward, north, south, okay? And then like this, okay? Now, if you can check there with your fingers, now this one here, this I'm gonna call it number one. This number one here, and then number two is for the field north to south. Now this number one here is for your middle finger, okay, but then pointing that way. Now hold them at 90 degrees to each other. We're going to find out that then the thumb is going to be going this way. It's going to be going down like this, okay. Now in that particular case, if you check what we have here, they're saying that the split rings rotate anti-clockwise. Okay. They say that the slip rings, they're saying the slip rings rotate anti-clockwise. This is not correct. The anti-clockwise is okay, but these are not slip. These are split rings, so it makes it to be wrong because they slip. Then they say now here for B, the clockwise is not correct because we see it's going down. So because it's going down to mean that it's going like this. Okay, and that's not clockwise. That is anti. Then the commutator rotate clockwise, that's not correct as well. So the answer would be what? The commutator rotate anti-clockwise. This is not the correct answer here. So the answer is D in this case. Okay. Let us move on now. They say which of the following statements is true for the photoelectric effect. Photoelectric effect, they are saying that demonstrates that the light has a wave nature, light has a particle nature, light energy is quantized. Okay. Now the light has a particle nature in the photons, okay, talked about. Then light energy is quantized, like quantums of energy packets. And so in this particular case, now the photoelectric effect does not show the wave nature. No, it shows these two. So it's gonna be 2 and 3. It's gonna be what? 2 and 3. Yeah. Let's proceed with our question 2 as we continue. Yeah, proceeding with question 2, they say here that in an experiment, a crate of mass 8.5 kg lying stationary on a rough horizontal table is connected to a mass hanger by means of a light inextensible string passing over a frictionless pulley as shown in the diagram below. The mass pieces are added to the mass hanger and the acceleration of the crate is measured. The experiment is repeated several times by adding different masses to increase the hanging mass each time. Ignore effects of air friction. I repeat, in an experiment, a crate of mass 8.5 kg lying stationary on a rough horizontal table is connected to a mass hanger by means of a light inextensible string passing over a frictionless pulley as shown in the diagram below. The mass pieces are added to the mass hanger and the acceleration of the crate is measured. The experiment is repeated several times by adding different masses to increase the hanging mass each time. So this is our 8.5 kg. This is the mass hung with the pieces. We keep on increasing the pieces here. Then the results obtained were used to draw the sketch graph below. So it's acceleration here on the y-axis. This is hanging mass, okay? Define the term static friction. Define the term static friction. You see, the word is static, it means it's not moving, né? And what do we know about friction? It opposes motion. And so, what's going to be our answer here? We say that that's the force that opposes the tendency. That opposes the tendency. Are we together? Of motion of a stationary object. Okay. So we're saying that static friction is the force that opposes the tendency of motion of what? A stationary object relative to the surface. Okay. Then they say here, draw a labeled triple diagram showing all the horizontal forces acting on the crate just before it starts to move. Okay. Now, guys, we're talking about horizontal. Okay, horizontal forces. Ne? I mean, don't put the vertical ones. Okay. So in here, I've got it's on here. Now they're saying before it starts to move. So here I have my horizontal forces. Now one force is pulling to the right. In that case, is what? It is the tension force. And at the same time, another force is pulling where? To the left, and that's what? The frictional force. And because it's not in motion, it's not moving, so I'm going to be having this side as my static frictional force, and then I've got what here? The tension force, okay? Then they say here that calculate the coefficient of static friction. Calculate what? The coefficient of static friction. Now what do we know? This mass is stationary. Are we together? And what's the mass here? The 4,2. So the 4,2 is what? Stationary here. Now here, just before it's moving, okay? Those are the masses which are being added. So we note our F net equals to MA. Our F net equals to MA, and it's going to be equal to 0 because it's stationary. So in this particular case, there is a FG here, and then the tension in here, okay? So in other words, I'm going to say that my FG minus tension T should give me 0. Now the mass is added were 4,5 here. So how do you find Fg? Mass times gravity, okay? Mass times gravity equals to my tension T. Then the mass is 4, what? It is 4,5, 4,2. So 4,2 multiplied by 9,8 to get my tension now. What do you get there? Calculators. 4,2 times 9,8. Here it gives me 41,16. I could get here 41,16. So this is 41,16 newtons. So this is my tension here. Now note that this added mass, yeah, that is just before it starts to move, and that's when we have the maximum static frictional force. Okay. Now this frictional force acting here, this point here, is gonna be Fs maximum. Okay. Fs what? Maximum. Fs maximum. So, and how do we now here we have the tension force with here as what? As the 41,16. Okay. Now I'm looking for the coefficient of what? Static frictional force, So we know that it is maximum static frictional force. Okay. It's maximum what? Static frictional force, and given by what? By the coefficient of static friction times F normal. Now the normal force is because of this mass here, the 8, what? 8,5, So it's gonna be given by what here? By the coefficient, okay? Then times, now the normal force is gonna be this mg here, that is 8,5 times 9,8. So this is 8,5 times what? 9,8. 9,8, okay? Times 9,8. 9,8 here. So now because it's not yet moving but almost to move, then this static frictional force maximum will be equal to what? Tension. So I'm going to equate these two now, okay? I'm going to equate these two here. So here I have the static key, this one here, coefficient of static friction times 8,5, okay, times 9,8 must be equal to the tension because it's not yet moving, eh? So that is what? That is the 41, what? 16. Okay, so here, if I divide it here, I'm gonna say 1,16 divided by what? By 8,5 times 9,8. So which answer do we get here? Which answer do we get here? Calculators. Here I'm getting 0,49. Okay, 0,49. 0,49. 0,49. Now this one is a ratio, so does not have units. Ne? Okay, that's what they wanted here. Let us proceed now. They say here that calculate the magnitude of the acceleration represented by y, this y here, on the graph if the coefficient of kinetic friction between the correct and the table is what? 0,4. Now, when the body is now in motion, now we call it what? Kinetic friction, okay? And the coefficient is what? 0,4. So what do we know? What do we know now? It's moving. So you know is what? F net equals to MA. We use F net equals to MA. We use our F net equals to MA. So F net equals to MA, okay? And why is it going? Why is it going? Because our FG or our tension, okay, minus Fk equals to MA. Okay, let us check properly. Now with this mass, it's accelerating, okay? That is accelerating now. Now the masses we have here, we no longer have 4,2, but instead we have what now here? We have now the 7, what? The 7,4. Okay, correspond this y here. Okay, so in this case, our Fg minus T equals to MA. Okay, our G minus T equals to MA. So the force of gravity minus 10T equals to MA. How do you find Fg? The 7,4, okay, 7,4, then times 9,8, 9,8 minus the tension T equals to MA, but the mass is what? The mass is 7,4, okay. Acceleration, so calculators here. What is 9,8 times 7,4? Times 7,4. Here it gives me 2,52. So this is 72,52 altogether. And then minus T equals to what? Equals to 7,4a. Are we together? We can say this is equation 1, right? But then that same tension here, which we have here now, will be the same tension here now. So it's no longer 41,16, but now it's bigger. So you're going to say that that tension minus the frictional force, which is now be kinetic, is no longer static, right? That's going to be kinetic now. So this is F kinetic here, then equals to MA. Okay, so again, our tension minus F kinetic equals to MA. So in this particular case, our tension here minus Fk, they give us coefficient. Now how do you find Fk? It is the coefficient kinetic times F normal, okay, equals to MA, okay, equals to MA. So they give us the coefficient here. So T, they give us 0, what? It is 0,4. Hope you can see it here. 0,4, okay, times normal force. So normal force, don't forget we have this 8,5 kg, 8,5 kg, and so it's gonna be the 8,5, okay, times 9,8, 9,8 equals to MA. Now the mass here is the 7,4, okay, the 7,4, 7,4, then times acceleration, which we don't know yet, okay. So if I multiply this now, what do I get here? If I multiply this, what do I get here? Calculators, what do you get here? Is don't forget that in this case, our mass is not 7,4, right? Because we're talking about the mass of the what of this one which we are pulling here. This tension for this one is the 8,5, né? And so this must be 8,5, not 7,4. This must be 8,5A. 8,5A. Don't forget we're looking for acceleration. Né? So from here, calculators, now what we have here, that is 0,4, okay? 0,4 times 8,5 times 9,8. Here I'm getting 33,32. So this is minus what? 33,32, 8,5A. Now our task is to find the acceleration. Ne? So now from our equation 1, this one here, we can see that our tension here, this tension ne, equals to 72 minus 7,4A, right? Equals to T. So this same tension is what I have here. I'm gonna substitute now. I'm gonna say it's gonna be now 70 what? 72, okay, 52 minus 7,4. Acceleration is the same, okay, equals, okay, then minus this one here, minus the 33, right, minus 33,32 equals to 8,5A. This one become a positive, ne? So now 8,5 plus 7,4, what do you get, guys? 8,5 plus 7,4. Here I'm getting 9. Getting what? 15,9A, okay. Now the 72,52 minus 33, 72,52 minus 33,32. Yeah, I get 39,2. So this is 39,2. So divided by 15, divided by 15,9, divided by 15,9. Okay. So what do you get here as your acceleration? Divided by 15,9 here. So it gives me my answer as 2,47. So acceleration is what? It is 2,47 meters per second squared. That's our answer. I hope we are together, guys. Let us proceed then. The last part of the question here. Question 2. What does it say? It says that, yeah, 2.4, they say a 5 kg block is now placed inside the crate and the experiment is repeated. How will this affect the maximum static frictional force now experienced by the what? By the crate. Choose from increases, decreases, or remain the same. Give a reason for the answer. Now, we know that our maximum static frictional force, okay, our maximum static is given by what? By the coefficient times normal force, okay. So if they add the 5 kg in the crate now, this is the crate here, this crate, if they add the 5 kg, then the normal force is going to increase. Normal force will increase, and because normal force increases, then this must also increase, ne? Must also what? Must also increase. So we say it increases because of the increase in the normal force, yet that maximum static friction is directly proportional to the normal force. The bigger the normal force, the bigger the frictional force. Okay, let's go to question 3. Question 3. Yeah, question 3, November 2024. It says that ball A thrown vertically upwards at 12 meters per second from the top of the building. 2 seconds after ball A was thrown upwards, ball B thrown vertically downwards at 5,4 meters per second from the top of the same building. Both balls A and B strike the ground at the same time 2 seconds. Ignore air friction. The position time graph is sketched below for the both of the balls. This is B, this is ball A. Using equations of motion only, calculate the value of each of the following as shown in the graphs here. They want t, z, and y. Now, I repeat, ball A thrown vertically upwards at 12 meters per second from the top of the building. You see it comes like this, okay? And then 2 seconds later, ball B is thrown vertically downwards, okay? But then at what speed? 5,4 meters per second. And then what's amazing, they all hit the ground at the same time, t. Then they say that calculate each of the following, the time t here. Now you see the two balls begin from the same level, meaning the same height, and meaning the same change in y. Okay, so from here to here, the same height, meaning the same level in y. Okay, this is our change in y. This is our displacement. Our change in y, our displacement. So it's the same for both balls A and B. So in this case, if we choose downwards as positive, okay, if we choose downwards as positive, then to get our t, okay, we're gonna do like this now. So our change in y for ball A, okay, change in y for ball A equals to v initial times change in time plus a half, ne, acceleration, then time squared. So for ball A, our change in y for ball A is gonna be, the v initial was 12, ne, but because it was upwards and we chose downwards, it's gonna be now negative 12 here, times change in time times t here, plus a half, okay, plus a half what? Plus a half here, plus 1 over 2 into 4,9, okay, or the 9,8 here, then times t squared. Okay, so from here, we can form the first equation. So we can say our change in y for the first ball A, which is our displacement, equals to negative 12t, okay, and then plus this is going to be 4,9 here. This is 4,9 t squared, and this is our equation 1. So they said 2 seconds later, meaning our time for ball B is going to be 2 seconds later, mean time t minus 2 because it is 2 seconds later. So the same formula, that's change in y now for ball what? For ball B will be given by the v initial for ball B times change in time, but now it's going to be t minus what? T minus 2. It's going to be t minus 2. This is v initial times t minus 2, okay? And then plus a half, okay? Acceleration, which is g, again t minus 2 squared, okay? So in here, now for ball B, the v initial is positive because it's thrown vertically downwards, so at 4 is going to be here, the positive 5,4, okay? And then here, our t is what? It's t minus 2, okay? Then plus here, 4,9 to get 4,9 here, then into what? Into t minus 2 squared, okay? So here, open brackets, we're gonna set it's gonna be here 5,4, okay, 5,4t. What about here? Minus 10,8, ne? This is 10,8, okay. What about here? Now when you square, it's gonna get t squared, ne? Then times 4,9 becomes 4,9t squared, okay. 4,9t squared minus 2, if that's minus 2 times t, that is 40. Now the 40 times 99, it gives us minus 19,6, minus 19,6, okay, 6t. Then plus 2 squared, which is 4. Now 4 times the 4,9 is also 19,6, but there's no t. So plus 19,6 here, plus 19 comma what comma plus 19 comma 6. Okay, plus 19 comma 6. So here plus 19 comma 6, and then now simplify here. I'm gonna get the 5 comma 4 5 comma 40. Okay, like times anyway, like times the 5 comma 40, right, minus 19 comma 60. What do you get? Calculator. The 5 comma 4 minus 19 comma 6. It gives me minus 14 comma 2. So this is minus 14 comma 2t minus 14 comma 2t. Now the negative 10 comma 8. Okay, the negative 10 comma 8, and then plus 19 comma 6 plus 19 comma 6. It gives me 8 comma 8. So this positive 8 comma 8, positive 8 comma 8. Then we have this 4 comma 90 squared, so plus 4 comma 90 squared. Okay, okay, so this is our change in y for ball B. Now this is equation 2 here. Now because it is the same height where the balls are initially projected from, I'm gonna equate equation what? Equation 1 to equation 2 because the height is the same, right? So I'm gonna say here that's minus 12, okay? Minus 12t, then plus 4 comma 9 plus 4 comma 9 t squared, okay, equals to negative 14 comma 2 t altogether, then plus 8 comma 8, and then plus 4 comma 9 t squared. 4 comma 9 t squared. Now if you see this in mathematics, the 4 comma 9 t squared is gonna cancel, right? It's the same, and it's an opposite of the equal sign, so it cancels out here. And then the minus 14 comma 2 become positive. Then minus 2 will give us 2 comma 2. So you have 2 comma 2t equals to 8 comma 8. So divided by 2 comma 2, our t becomes 4. So it is 4 seconds. Our t becomes 4 seconds. So that's our t which they wanted here. I hope guys we are together. So our t is 4. Our t is 4 here. Now they also say find our z. Now z is the initial height, so I can use the one for the first equation 1 because now I know the t, which is 4. So it has get for me this now. We can substitute it now and see. We can say that in this case our z is gonna be what? So here we have what? Remember we have here the negative 12t. So we have negative here, negative 12. Our t is the 4, okay, and then plus 4 comma 9 t squared plus 4 comma 9 t squared. But our t is the 4 squared in this case, which gives us the 30 comma what? 30 comma 4. So our answer is 30 comma 4 meters. It is 30 comma 4 meters. 30 comma 4 meters. That's our z. It is 30 comma 4 meters. 30 comma 4 meters. Okay. Then our y here. Now the y is maximum height here. Now the maximum height reached by ball A, because you know the initial velocity, which is 12. So what happens at maximum height? Velocity is looking for that y. Okay, so if I'm gonna use v final squared, okay, equals to v initial squared plus 2a. I'm changing y, okay. So it's gonna be 0 at maximum height. What about initial was negative 12 squared, okay, and then plus 2a. Our 8 is positive 9 comma 8 because we chose that one as positive. We're looking for this small h here, okay, the small h from y to z. Okay, so this is 144, which become negative 144 this side. 144 equals to 19.6, 19.6 h. So divided by 19.6 here, what do you get? Divided by 19.6 here, what do we get here? So our small height h is going to be 144 divided by 19.6, 19.6 here. It gives us, we're getting here 7, what? Here 7.35, 7.35, okay? So this 7.35, I'm gonna add it to this other one, which is 30.4 to get my y. So plus 30.4 plus 30.4, which gives me 37.75. So my z, my y is 30 what? Is 37.75 meters, okay? Yeah, guys, I hope we are still together here. Now they say that on the same set of axes, sketch real time graphs of the ball A and the ball B while they are in free fall. Label the graphs A and B for ball A and ball B respectively. Clearly indicate the following on the graph C: the initial velocity of each ball, the time at which each ball is thrown, the time at which the ball strikes the ground. Okay, hope we are together. Let us proceed. Now here, what we have to understand is that the two balls, they are under free fall, né? And because we are looking for the velocity time graph, okay, this is velocity versus time graph, né? We're gonna have our velocity here in meters per what? Meters per second. This is time in seconds here. So our choice was down as positive, né? You remember that? Which means our ball A was winning somewhere in the negative because it was negative 12, né? So our ball A is gonna be like this now, okay? Our ball A, let's take it like this from here now. If this is my ball A, now ball A is the initial was what? 12, né? So being a 12, it means that, and because I chose down as positive, né? It must be like this now. It must be a negative initial velocity. Okay. And then the study must indicate what on the graph? Initial velocity of each ball, né? Here. So this was negative 12. Okay. And then at maximum height here, velocity is 0. All together. So you're reaching maximum height, né? Somewhere here. And then don't forget our time was for what? It was 4 seconds for all the balls. So it means on here, but at 4 here, this is the 4 seconds here. Are we together? Now they said that so if it's up here, they said 2 seconds later, that's when ball B was thrown vertical downwards. Né? Now because we chose down as positive, now our ball B is 2 seconds. It is somewhere here, halfway somewhere here. Okay. If I can select this now, so my other ball, okay, the ball B, let me use now the red one here. If it is a ball B, now they are under free fall, né? So they must have the same gradient. The same gradient, must be like some gradient here, okay? And because it's also at the same time, it means that they don't go beyond the 4 here, so must stop at 4 here. But however, not the case, my V initial for that other ball now, which is ball B, it is a 5.4, né? So this line here, this one must be 5.4 here, where I have my B what? My B this ball here. So this is 5.4 meters per second. Then the time, it was 2 seconds later, so this is a 2 here. Okay, so this is ball A and this is ball B. Okay, anything left behind? I don't think so. Meters per second, time in seconds. So this is ball A, ball B. Yes, so that's what they wanted here. This don't know what 5.4 corresponding here, né? That is the initial for the ball B. Here it was negative 12 for ball A because we said down is positive. Okay. Let us proceed. Next question. Then, next question here. What does it say? What does it say here? Question 4, November 2024. It says that the two trolleys A and B of masses 1,5 kg and 2 kg respectively, they are held stationary position on a straight horizontal frictionless track with a compressed spring between them. The trolleys are released and the spring takes t seconds to return to its natural length. The spring then falls to the ground. We see it is here. The ground here was compressed. Trolley A moves to the left, okay, to the left, and while trolley B moves to the right, then up a frictionless inclined plane, rising to maximum vertical height of what 1,4 meters, as shown in the diagram below. Ignore air friction and the rotation effects of the wheels. Write down the principle of conservation of mechanical energy in words. Okay, I repeat, the two trolleys A and B of masses 1,5 kg and 2 kg respectively, they are held stationary positionally on a straight horizontal frictionless track, okay, with a compressed spring between them. The trolleys are released and the spring takes t seconds to return to its natural length. The spring then falls to the ground. Trolley A moves to the left, what about B to the right, and then up a frictionless inclined plane, rising to a maximum vertical height of what? 1,5 meters shown the diagram below. So here before the spring was released, here the spring has been released and trolley B moves up the incline and stops on what? 1,5 meters, okay? Then they say write down the principle of conservation of mechanical energy in words. The total mechanical energy in an isolated system is conserved. That's how I write it, okay? The total mechanical energy in an isolated system is what? Is conserved, okay? Then they say, calculate the speed of trolley B at the bottom of the inclined plane. Calculate what? The speed of trolley B at this place here, at the bottom here, at this point here. Okay. Now, because I don't know about anything to do with the V initial for trolley A and B what and B final, so I'm gonna use mechanical energy conservation. So, because there was of 1,5 meters, now to do with my trolley B, okay, my trolley B, I will say that E mechanical, let me say this, if this is the bottom here, E mechanical at the bottom, this is the top here, ne? Top here. E mechanical at the bottom, okay, bottom is equal to E mechanical at the top. E mechanical at the top. Now, what is E mechanical? It's the sum of EK and EP, okay? When you add the EK plus EP for trolley B, okay, you get mechanical energy, ne? Even here, EK plus what? Plus EP, okay, for the trolley B. Now, EP on the ground here, because the height is 0 on the ground, the EP is going to be 0. What is MGH? Ne? Don't forget. The height is 0. So if we talk about MGH here, MGH, n plus a half, okay, m v squared, okay, at the bottom here, equals to a half, okay, m b squared plus mgh here as well. So now the mass of trolley B, it is 2 kg from here. I'm gonna say 2 multiplied by 9,8, okay. Now at the bottom, the height is 0, okay. So plus 1 over 2, the mass is still 2, okay. I want this velocity here, ne? At the bottom, and then equals to 1 over 2, the mass is still 2, and then velocity is 0 at maximum height here, ne? Velocity is 0 here. So n plus mgh, the mass is 2, times 9,8, okay, times 9,8 times 9,8 times 9,8. So here, um, times 9,8. So here, it means that I'm gonna say here times 9,8, okay. The height here, which we see it is 1,5, né? You see it here, 1,5 meters, okay. So from this information here, I'm gonna be having a 0 here. Now the 2's are gonna cancel here, leaving me with the velocity squared at the bottom, okay, equals to, gonna be a 0 here as because of this 0. Then the 2 times 9,8 times 1,5, what do I get here? So 2 times 9,8 then times 1,5 gives me 29,4. So this 29,4 here, and I'm looking for my v, okay, 29,4 here. Then square root that, square root here of this answer. I'm getting 5,42. So arbitrary b at the bottom is 5,42. It is 5,42 meters per second to the right, okay, to the right, okay. I hope we are together. Let us continue here. Then they said that then here for the time t seconds the spring takes to return to its original natural length, calculate the change in momentum of trolley B. Okay. Now how do I get change in momentum? How do I get change in momentum here? What do we know? What do we know, guys? Change in momentum, that is 4.3.1. Now our change in momentum equals to final momentum, okay, minus what? Initial momentum means V final minus V initial, okay, divided by, yeah, that is it. So now the mass of ball B, block B is what? Is 2. Now at this point, at max, at the on the top of the need at the tree at the bottom of the incline is the B final. In this case, which is the 5,42. So it is 5,42, okay. And because they were initially held at rest, it means my V initial is 0, right? So it's minus 0 here. What do you get here? So the 5,42 times 2, 2 times 5,42 here, it gives me 10,84. So this is 10,84, 10,84. Now this is my change in momentum here, which is also measured in what? Meters per second, okay? So 10,84, you can say kilometers per second, and it is to the what? To the right, okay? To the right. All right, that's our answer here. That's our momentum for what? For the trolley B, or for mass B. Let us continue here. Let's write down the change in momentum for trolley A. Now, this moment for the two trolleys after separation, they are gonna be equal. Why? If body A exerts a force on body B, then body B exerts the same force on body A with the same one, but opposite direction. So although trolley A goes to the left, it's gonna be having the same momentum, but to the what? To the left. So here you're gonna say also that's 4.3.2, 4.3.2 here, that the change in momentum for our trolley A is going to be the same as what? The 10,84 kilograms per second, okay? But now this time we don't sort to the right, we say to the left. Okay, that's our answer here. Now they say that calculate the speed of the trolley A after 30 seconds. Calculate what? The speed of trolley after 30 seconds. Now trolley A, we know it went this other side, this side here. But we know that because we have the change in momentum, then we are gonna use it now. Okay. What do we say here? That our change in momentum for trolley A, okay, for trolley A equals to mass, okay, no velocity altogether minus what? Minus initial velocity. Now the change in momentum there we got the 10 comma what? It is 10,84 as well. So I'm gonna say here 10,84. This is 10,84 negative 10,84, and then the mass was given as 1,5. Okay, and then now the final velocity here, v final is what I'm looking for. No, it's what, yeah, that's what I'm looking for here. And initial, it was 0, so minus 0 here. And then so what do we have here? We're gonna have negative 10,84 equals to 1,5 v final. Okay. Now this v initial is 0 because they were initially held at rest. That's why the v initial is 0. So divide by 1,5 divided by 1,5 here. So our speed, which is magnitude of velocity, so 10,84 divided by 1,5, what do I get here? Divided by 1,5 here, it gives me 7,73. So my speed here is 7,23 meters per second. Now here I ignore the negative because I'm looking for speed. Looking for speed. Let us proceed, guys. Let us proceed. Next question here. Question 5, it says here that a constant force F is applied at an angle of 30 degrees to the horizontal on a crate of mass 6 kg that is initially at rest as shown in the diagram below. A constant frictional force of 10 newtons acts on the crate as it moves from rest at point A along a horizontal surface at point B. The distance between points A and B is 1,5 meters, and the speed of the crate at point B is 2 meters per second. Okay. Define the term work done by the force. So how do you define work done by the force? Now, our definition of the work done, we know that first of all, our work done W, work done W altogether times displacement times cos of what? Cos of theta. So from this equation, we can define by saying that the work done is the product, meaning multiplication, altogether. We say that work done on an object is what? Product of the force, this force here, and the displacement, and the what? Displacement of the object in the direction, in the what? In the direction of the displacement. I repeat, we're saying that work done, okay, work done is what? Is the product, write it down here, is the product, okay, I'm gonna say the product, I'm using because of multiplication, that's why I'm saying product. I'm saying the product is the product altogether of the force, of the force, of the force, of the force on the what? Product of the force and displacement, and the displacement of the object, in the direction, of what? Of the displacement, in the what? Direction of displacement, in the direction of displacement. Okay, so work done is the product of the force and the displacement of the object in the direction of the displacement. Okay, hope we are together, guys. Hope we are together. Let us proceed. Next here, they said that what must we do next? Okay, what should we do now? Let's draw a labeled freeboard diagram showing all the forces acting on the crate as it moves, not only horizontal like before, but all the forces acting on the crate. So they're giving us 4 marks here. And so we're going to be having 4 arrows coming from the dot. Now this box, all these objects on the surface, horizontal. So you have got weight, then normal force, then this friction of 10 newtons, which they gave us here. So now because it's going to the right, friction is opposing the motion. And so for that matter, my free body diagram would look like this one here. So I'm going to say I have this one, okay, this one here is my free body diagram here. The free body diagram here, and let me just make it blue. So I have the applied force at an angle. See, I'm gonna have here the weight and the normal force of, okay, weight and normal force, and then opposed by frictional force, right? So the frictional force is going this way now. Okay, frictional force going this way, and then don't forget that we have the applied force at what? At an angle, at an angle. So applied force at an angle, you see it here, this force here. Put it like this now. An angle, okay. Oh, angle like this. Okay, so this is what I have here. So in other words, that's my free body diagram. So here I have my frictional force, which is kinetic frictional force. Okay, this is the weight here. You can say W, you can say Fg. This is our normal force, which is Fn. Okay, apply the force here, which gave us as F. This is 30 degrees, so my 30 will be somewhere here, but even if I don't indicate here, it doesn't matter. Okay, that's what they wanted here. Now they said next that we should do what here? Use energy principles only, calculate the magnitude of the what? Of the force F. So I want this force F here. All right, so I'm gonna use work net equal to change in EK. I'm gonna use what? Work net equals to change in EK. The net work done equals to change in the object is G. Okay. So here I have this component here going this way. Okay, this force I have. Now it means I'm gonna have the work done by that force there plus work by frictional force. Okay, so to give me change in EK, that means I have, okay, into I have M, that means I have times the mass. Okay, I have times the mass into final velocity squared minus V initial here. I'm gonna say that now how to find work done by the force F? It must be the force times what? Displacement times cos of theta. So I'm gonna say here the force F altogether times displacement times cos of theta. I'm gonna get the weight done by that force, okay? Then plus what? Frictional force times displacement times cos of theta as well. So equals to I have, see what? Final velocity minus initial velocity, okay? Final what? Velocity minus initial velocity. So this is V final minus V initial here. Okay, square, don't forget square here. So the force I'm looking for this force F. What about our displacement? They say how many meters from A to B? They gave us 1,5. So it's 1,5 here. So times 1,5, 1,5 here. What about our theta? It is 30. Then cos of 30. Okay. Now friction, they gave us 10. Hope you can see it here. They gave us 10. It is 10 newtons here. Okay. And let's say plus 10. Okay. Plus 10. They have the same displacement 1,5. Okay. And then our theta for friction is what? 180. So cos 180 here equals to a half times the mass. Do you know the mass of the crate? It is 6 kg. Okay, that is 6 kg there. So open brackets here. Now they gave us the final speed at point B, What speed was that? They gave us, they said it is 2 meters per second. It was from rest, ne? So it can be 2 meters here squared. Okay, 2 squared here minus 0 squared. Okay. So calculators here, what do you get now? Um, this one here is gonna give me minus 15, right? So here I have minus 15. Okay. What about the side here? I'm gonna have the cos of 30 and then 1,5. What does it give me? 1,5 cos t. It gives me 3 root 3 over 4. Ne? I have 3 root 3 divided by 4 times f. Okay. Now this side, I have the 3 here times 4, which is 12, right? Which is 12. Now plus 15, it makes 20 what? 27, right? So I'm now, because I'm looking for the force F, I'm going to multiply by what? I multiplied 27 by what? By 4, right? Multiply 27 by 4. And then I divide by 3 root 3, okay? So multiply 27 here by 4. Divided by what? By 3 root 3. So our force F is given by what here? Calculators again. Let's check it here. So 27 multiplied by 4 divided by 3 root 3. Here it gives me 20,78. 20 newtons. 20,780 newtons. I hope we are together. That was our question there. Then they say here again on question 5 that a 2 kg object is placed in the crate. What effect will this have on the work done by the same force F when the crate is again moved from point A to point B? Write only increase, decreases, or remain the same. So what do you think here? I repeat, they say here that a 2 kg object is applied on the crate. What effect will this have on the work done by the same force when the crate is again moved from point A to point B? Write only increases, decreases, or remain the same. So here we say it's going to remain the same. It's going to remain the same. Why? We have the same force and we have the same what? We have the same displacement and the same angle. So what do you expect? Same force, same displacement. So it will be the same work done because work done is what? Times displacement all together in the what? Direction of the displacement. Okay, next question here. Question 6. Question 6. Let us proceed with it now. Question 6 says, yes, my friends, question 6, it says that a stationary listener standing on the roadside records a wavelength of the sound emitted by the siren of a police car traveling at a constant velocity. In the wavelength time graph below, not drawn to scale, lambda L is the wavelength of the sound recorded by the listener, and lambda S is the wavelength of the sound emitted by the siren. So the speed of sound in the speed of sound in the air is what? 340 meters per second. Now what do you have on the y-axis here is wavelength. It's not frequency but wavelength. Ne? The lambda L listener, lambda S from the siren or sound source. Name the phenomenon that explains why wavelengths shown in the graph differ. Because of what? Doppler effect. Okay. Is the car moving towards or away from the listener? Give a reason for it for the answer. Now from Doppler equation, what do we know? What do we know from Doppler equation? That our F listener, right? Our F listener equals to V plus or minus together V listener divided by V plus or minus V source times what? Times frequency of the source. Ne? Now we know that from this equation here, if the frequency of listener is greater than ne, the frequency of the source, then either the source is moving towards the listener or listener moving towards the source. Ne? But that's for the frequency altogether. Now in this question here, now we have the wavelength of the listener being greater than wavelength of the source. Okay. Now for this one here, if it is frequency, we say we are moving towards this, towards what? Towards the sound source. However, this is now wavelength. Wavelength is the reciprocal or the inverse of the what? Of frequency. I mean that the higher the wavelength, the lower the frequency. Actually, from here, it should indicate to us that the frequency now of the listener is going to be less than frequency sound source. And so we say what? It's moving, it is away from, because we see that in this case, frequency of the listener is what? Less than frequency of the listener. But they say give a reason here. They're going to say because now the wavelength of the listener is bigger than wavelength of the sound source. Okay, then let's calculate the frequency of the sound emitted by the siren. Now we know that our V, speed of sound, equals frequency times lambda. So here, now the V here is 3 what? 340, 343 given to us here. And then you're looking for the frequency, né? Looking for the frequency of the source. Okay, that's the F source here. Then times, now we have lambda source, which is 0.38. So 0.38. Now if you divide here, our F source is going to be what? The 343, okay, divided by what? 0.38, 0.38. So what do we get here now? What do we get here? The 340 divided by 0.38. So 343 divided by 0.38, né? It gives us 902.63. So you have 902.63. Now this is that's our frequency for the source. Okay. All right. Next question here. They want the magnitude of velocity of the car. We're looking for the V source, né? Now because we are having a stationary listener and is moving away, the siren is moving away, this equation here is going to become what now? It means that we're going to say the frequency of the listener equals to V, because it's moving away, we're going to say minus V listener divided by V plus V what? Plus V source times frequency of this now. Okay. So in here, we have the frequency, we're going to get frequency of the listener as well by dividing the that the 343, okay, divided by 0.4. What do you get now? Divided by 0. It gives us what here? Let me check here. 340 divided by 0.4. 343 divided by 0.4. Yeah, it gives me 857.5. It is 8 what? 857, 85, comma 5 equals to this speed they gave us. It is what? 343. Okay, 343. Then minus 0, because this one is stationary, divided by 343. Okay, then plus V of the source. So that's what we're looking for. Then the frequency here we got 9 what? We got 902.6 what? 63. So from here, our calculations, what we do here in this case, I'm gonna say that the 343, okay, the 3 plus V source equals to 343, okay, multiplied by 90 what? 902.63 divided by what? Divided by 857,5, okay? And so then later I'm gonna say minus what? Minus 343. Minus 343. So my speed for the siren is gonna be what? Calculators there. Get me the answer, please. Calculator there. Yeah, it gives me here 18,05. 18,05. So here, that's my answer. It is 18,05. Okay, 18,05 meters per second. That's the speed of the siren, guys. Hope we are together. Let us go to question 7 now. That was question 6. Question 7. Question 7. What are we supposed to do with question 7? Okay. All right. Question 7 says here that P is a point positive to nanocoulomb point charge. X is a point 6 centimeters away from charge P as shown in the diagram below. Calculate the magnitude of the electric field at X. So we want the electric field at point X here, and we have the source charge, okay? So if you have the source charge and the distance here, and you're looking for your E, electric field at that point X, then use this formula here. Then you're going to use E equals to KQ divided by R squared, okay? So here, yes, so I'm going to use it here now. But what does nanocoulomb mean to us? Times 10 power negative 9, okay? So looking for our E here, 7.1, our E 7.1, our E. You know that our E equals to K, okay, equals to K times the charge Q by the distance here. So here, now our K is 9 times 10 power 9, right? 9 times 10 to the power 9. Then the charge given here is positive 2, that's 2. Now nano is times 10 power negative 9, okay? Then divided by what? Distance, which is, now these are centimeters, ne? What did we put? Meters divided by what? Divided by 100, then must square. So 0,06, that must be squared, ne? Okay, so here, what's going to be your E? Calculators. Here it gives me 5,000. So here I have 5,000, and this is what? Newtons per coulomb. This is 5,000 newtons per coulomb. 5,000 newtons per what? Per coulomb. Okay, so that's our E. Then they say here that S with a charge in negative 2 nanocoulombs is placed 4 centimeters to the right of charge P, as shown in the diagram below. This point charge S. Draw the resultant electric field pattern due to charges P and S. Now our P is positively charged. What about S? Negatively charged. And as you can see, they have the same magnitude. And because they are oppositely charged, they're going to be attracting, okay? And so for that matter, this is what you're supposed to draw here. Okay, so we're going to draw here. Now, guys, note when you're drawing, you don't need to, okay? As long as you indicate your point charge, okay? Indicate your charge here, and then this P is positive, and then put a positive here. Then the other one is S, put a negative here. Are we together? So now, begin with this line here. It's going to be like this, okay? And then another one here. Then was not touch inside or not go inside, okay? You go like this from the surface of the sphere, to the next surface, okay? I don't know it wants to get inside here, like that. Then now this is attracting, so like this, another one like this. Draw them tangential if possible. Okay, like this now, and like on here. So don't draw so many because if they cross, you lose a mark. So this one is fine here. Now note that we use a positive test charge, né? A positive test charge. So if I put it here, it will go to the negative like this, negative like this. So the negatives, they go inwards. What about the positive? Outwards. Let's also negative here like this, even here like this. No, outwards. Now this is positive, outwards for positive. So positive, they point outwards, so like this, pointing outwards like this, and like this. Okay, so that's our resultant electric field pattern due to charges P and S. There is also that 4.3, a third one, I say here, a 30-point charge T is placed 2 centimeters to the right of S, as shown in the diagram below. Point charge T experiences a net force of what? When it turn to the left. Not this. This is the net force experienced by this charge T here. Is 2,5 times 10 power negative when it turns to the left. Okay. Coulomb's law in words. How do we state it? How do we state Coulomb's law in words, guys? State it for me to avoid practicing tomorrow. How do we say it? The magnitude of the electrostatic force which is exerted by one point charge on another point charge is directly proportional to the product of the magnitudes of their charges and inversely proportional to the square of what? Square of distance between them. Okay. Square of distance between them. Okay, then they say here that what's the polarity of the charge T? Choose from positive or negative. Now, because it is being attracted to the left here, means that it's being pulled by this negative. So our T must be what? So we say that our T is going to be what? Positive. It's positive here as our answer. Then they say calculate what? The magnitude of the charge T. They want magnitude of the charge what? Charge T. So in that particular case, and so because they said to the left here is our resultant, so the net force at T of the two charges at P and S. So meaning that our charge or our net force at point P, okay, on this T here, F net on T, okay, is gonna be the force because of charge S on T altogether plus the force because of charge what? Charge P on T as well. And in this particular case, from Coulomb's equation, now each force is given by K times the charge on S times the charge on T divided by the distance R squared here. What about here? Then plus the force again here, the force which is K times charge on P or the charge on T divided by what? Our distance squared. Okay, so let us now substitute here. Now the K does not change. It's 9 times 10 power 9. Okay, power 9. Now the charge on S we know it is 2. Non-equal is going to be 2 times 10 power negative 9. Okay. 9 times the charge on T which we are looking for. Okay. Our distance from T to S is how many meters? It's 2 centimeters. So divide by square. So that's going to be 0, 0,02, 0,02 squared. Okay. What now? We have again plus here. Our K does not change. That is 9 times 10 to the power 9. Okay. And then times the charge on P, which is also happening to be 2 times 10 to the power negative 9, okay? All together. And then our distance from P to T is what? It is 6, 4 plus 2, which is 6, ne? Also, the charge on T, the charge on T which you're looking for, okay? What about our distance now? It is what? It is 6 centimeters, ne? It becomes 0, 0.06 squared, okay? Squared here. Now, because they say to the left, if we choose positive as right as positive, then this answer, this one I'm gonna make it negative because they say to the left, ne? So I'm gonna say negative 2,5, okay? Negative 2, what? 2,5 times 10 power negative 4 times 10 power negative what? Negative 4 here. Okay, so then let us think this through. Now check this out, guys. Now between S and T all together, it is a force of attraction, meaning that it's going to be pulling the T to the what? To the leftness. So this I'm going to make it negative as well. Between S and T is going to be negative here. Okay, and then the P and the T, P and the T. Remember, T is positive, ne? It's going to be a force of repulsion. So it's going to be negative. It's going to be pushing the T to the right, and so that force will be force of repulsion, repelling T to the right, and so here. So it's positive. Okay. So now my calculations now, if I simplify this one here, I can see here that this one it can cancel out, ne? This one, right, guys? This one, and then they cancel out. 9 times 2, I get 18. So 18 divided by what? 18 divided by 0, 0.02 squared. It gives me here 45,000. So here I have negative 45,000. Okay, QT. Don't forget I'm looking for byte. I don't forget that. What about here? Positive what now? Now again here I cancel this one here with this one here. It cancels out. So this is 9 times 2, which gives me 18 again. Now divided by what? Divided by 0, 0.06 squared. Okay. Here it gives me now 5,000. I get 5,000. Okay. 5,000. Again, Q what? QT. I have negative what side? Equals to negative 2, what? 2,5. Okay. Times 10 power negative 4. Now, if you look at the negative 45,000 minus 5,000, I'm left with negative 40,000. Okay. So here, if I divide by negative 40,000 both sides, I decide I'm gonna have now the negative 2, 5, okay, times 10 power negative 4 divided by negative 40,000, negative 40,000, okay. What do you get here? Our charge of T. Calculators. What do you get here? I'm gonna say here it is the 2,5 exponent negative 4 divided by 40,000. Okay. Yeah, it gives me 6,25, okay, times 10 to the power negative 9 coulombs. Okay. Yeah, that's my charge on T. It is positive 6,25 times 10 to the power negative 9 coulombs. Together, let's go to question 8. Question. They said that L1 and L2, there are two light bulbs that have this following rating, that is L1 36 watts, 20 volts, L2 is 48 watts, and the two bulbs are connected as shown in the circuit diagram below. The battery has an internal resistance of 0.6 ohms, while the conducting wires and the ammeters have negligible resistance. R1 and R2, this one is here, are resistors. Okay, so with ammeter 1, A1 here, Ammeter A2 here, resistor 1, resistor 2, which is 4 ohms. They say here that define the term power. Power is what? The rate at which work is done. They say that if both light bulbs, now if that, it means that they're gonna use what? They're gonna give out 36 watts power voltage of what? They use voltage of 20 volts for L1. What about light bulb 2? The power of what? Of 48 watts and the voltage of what? 32 volts. Okay, they say calculate the reading on ammeter A2. Now ammeter A2 comes from light bulb L2. So I'm gonna, because I've got the power for L2 and I have the voltage, I can get the current so that my A2, which is I2, I can find it. So I'm gonna use P equals to VI, okay? That is 8 point what? 0.2.1. I'm gonna use what? P equals to VI. I know the power, okay? And then I know the V, looking for the current I. So the power given here on light bulb is 48. I'm gonna say 48 here. 48 watts, okay? What about the voltage? They gave us 32, okay? Now the current here, because it's for light bulb for ammeter A2, I'm gonna call it I2, okay? Call it I2 here. So divide here, guys, what do you get? Divided by 32, divided by 32. What's gonna be our I2 here? So our I2 here will be what? So 48 divided by 32, it gives us here 1,5 amperes. So this 1, here 1,5 amperes. Okay. Next, okay, so now reading on ammeter A1. Now ammeter A1 is this one here. Now I know the current I2 here, which is 1,5, ne? Okay, 1,5 amperes. And then I don't know for this one now passing here. Now I'm gonna call it now because I have the ratings for L1 as well, I can get my current. I'm gonna call it current I3. This is I1, but it's going to be I3 here. So to get my I3, because I know this one operates as rated, I know if again I say that my P equals to V times I, this time I'm talking about I3, right guys, I3. I know the power given to me is what? It is 36. I'm gonna say 36 now, okay? 36. What about the given V? They gave us 20. Then times I3. Times I3. So divided by 20. Divided by what? Divided by 20. And divided by 20 side as well. So divided by 20. So my current I3 is gonna be 1,8, right? 36 divided by what? By 20 is 1,8. So my current I3 is gonna be 1,8. So now the I3 is just part of the branches, so 1,80 amperes. Now to get my I1 from the ammeter A1, I1 equals to the branch that is I2 plus I3. What do you get, guys? Plus I3 here. So if I add the 1,5 plus 1,8, what do I get? Plus 1,5. It gives me here 3,3 amperes. So I get what here? 3,3 amperes. Okay, that's my I3. Reading on ammeter A1 is 3,3 amperes. 3 amperes. Okay. What about here? 1,5 amperes. Okay. Next question says what now? They say that now resistance for resistor R1. Now, guys, note that my resistor R1 is what you see here. Now, guys, also bulbs, they are also resistors, ne? So, resistor R1 and light bulb 1 combined, I can find my total resistance, ne? But however, note that the light bulb L2 is in parallel with this combination. So, because of that, the voltage for light bulb L2 is the same as the voltage combined here. Why? Because they are in parallel. So note that in that particular case, I'm gonna do like this now. I'm gonna say that the voltage of light bulb L2 is equal to the voltage of resistor 1 and L1. Okay. Why? Because they are in parallel, so the voltage of light bulb L2, okay, is the same as what? The voltage of light bulb L1 plus the voltage across resistor what? Resistor 1, which I'm looking for. Now VL2, I know they gave us what here? If you just check up here, they gave us um 32. This one here. So I'm gonna say 32. What about VL1? They gave us 20. 20 here. Now how do you find the VR1? Get the current, which in this case we call the I3, okay, times what? Resistor 1. Okay. So now the 32 minus 20, I get 12, okay, equals to my I3 was 1,8, ne? 1,8, then times resistor 1. Resistor 1 here. So I divide the 12 now by 1,8. What do you get here? Divide by 1,8. Divide by 1,8 as well here. So my resistor 1, if I divide 12 by 1,8, it gives me 6,67. So my resistor 1 is what? 6,67. It is 60,67 ohms. So here it is what? 6,67 ohms. Okay. Next, what are they saying here? They want EMF for the EMF of the battery. Now the EMF, because I know the resistance, okay, and I know the total current passing through I1. What else do I know here? I know that I know that my formula, get some space here. Now EMF equals to the total current I into total resistance plus internal resistance. But if I open the brackets, what do I get? I get my EMF. Get what? My EMF. Come on. My mark. I get my EMF as what? Oh no, guys. Yeah. My EMF. Come on. EMF ne, equals to total current I. Open brackets here. Total what? R external plus R internal ne. But brackets here. The EMF ne, the same as I times R, which is V external, ne? V external altogether, V external plus V internal, which sometimes we call the lost volts, ne? Lost volts or V internal. So now the V external is the V across right bulb R, across resistor R2 plus the V parallel here now. Okay, plus this V parallel. If I may combine this one here up to here, and I put my voltmeter here, it will be V parallel on it. So it's gonna be the V parallel plus the V across resistor R2, then plus the V internal, and then I'm gonna have my what? My EMF. Okay, so now the V parallel the same as the V across light bulb L2 because they're in parallel. So I'm gonna take what? Take the 32, gonna be 32 here. For the V parallel, gonna be 32 here. What about VR2? I know total current passing is we got 3,3, ne? I'm gonna say remember it's IR2 here, ne? I times what? Resistor 2. So I'm gonna say here the I is 3,3, right? 3,3. What about resistor R2? They gave us 4. and then plus, what about here in the V internal? Again, I also say I, which is 3 comma 3 times what? Times the given internal resistance, which is 0 comma 6 here. Okay, so 0 comma 6 here, 0 comma 6 here. And then now, what's my final answer here? Calculators, come on, come on, come on. We have 32 plus, open bracket, 3 comma 3 times what? Times 4, close bracket. 3 comma 3 times 0 comma 6, close bracket. Now, final answer is going to be what here? I see it is 47,18. It is 47,18. Okay, now there are so many methods of doing this. This is one of them, and I hope that you've understood. Next question here, they say what now? They say that bulb L1 burns out after a while. Assume that the resistance of bulb L2 remains constant. Will bulb L2 continue to glow after bulb L1 burns out? Choose from yes or no. Support your answer with a suitable calculation. I repeat, the bulb L1 burns out. This one here, L1 burns out. And then, after a while, assume that the resistance of bulb L2 remains constant. This one here remains constant. Will bulb L2 continue to glow after bulb L1 burns out? Choose from yes or no and support your answer with a suitable calculation. Now, they said that they operate as rated. You see it here? They do what? They operate as rated. So because of that, in that this light bulb L2 will only work if the current passing here is 1,5 amperes. Are we together? So I'm going to find out now the total current remaining. If that current is bigger than 1,5, bulb L2 will not work. If less, it will not work. So I'm going to find out now. When this resistor, when this one is burnt out, it means resistor R1 and L1, they are all out of action now. Now my current is only passing here like this. My current is only passing where? It's only passing here like this now. Only passing here. So our current only comes like this from only passes here like this now. Because our thing for L1 is burnt out. So this is now the circuit which we have now. So now in here, as you can see, this one is in a series, the 4 ohm in a series with this light bulb L2. Let me find the resistance now. Now again, because I have the power for light bulb L2, I can find its resistance, right? By what? By using a P equals to V squared over R. By using what? By using a P equals V squared over R. Let us go ahead here and do that now. So if I come here now to get my L2, okay, come on. What I'm gonna say P equals to V squared, okay, equals to V squared over what? Over resistance here. Now the P here they give me it is 40 what? It is 48, don't forget. So 48 here, 48 equals to V squared, which is 32 squared again, divided by resistance of the bulb L1, okay? So rather L2. So in here, my resistance 2, if I do cross multiply here, I'm gonna say 32 squared divided by what? Divided by 48. So which answer do we get here? Calculators, 32 squared, 32 squared divided by what? By 48. Here it gives me 21,33. So I'm getting 21,33. Okay, ohms. Now to get my total current here, I know the EMF. I'm going to say that EMF, okay, equals to what? Equals to the total current, which I don't know yet, divided by the R external plus R internal. Now, because EMF is a constant, I can find my what? My current I to see if it is the same as 1,5. If not, then the bulb will not glow. Are we together? Bulb will not do what? Will not glow. Okay, so for that matter, I'm gonna say, maybe I already know my EMF, ne? I know my EMF already. How much is it? It was 40 what? 40 something, 47,8, right? 0,18, ne? Say here, it was 47, so it's 47,1. Okay, so 47,18, okay, is equal, I'm looking for this current here, the current I. Now my R here is the same as this 21, what? The 21,33, right? And then also plus what? Plus this 4 here, plus the 4 ohms. Then the other internal given to us was 0, what? 0,6. Okay, so then and I get my current I here. If I divide this, so calculators, please get me the answer. Now, the 47,18 divided by 21,33 plus 4 plus 0,6. Here it gives me 1,82. 1,82. Now, 1,82 amperes is more than the 1,5 which is required. So, light bulb L2 will not glow. So, we say a no. We say no here. Why? Because now the current is too much. Now, because the 1,2 is greater than the required 1,5 amperes for the light bulb to operate. Remember, they said that these bulbs, they do what? They operate as rated. With more current, they don't. With less, they don't. So only operate as rated. So we say it is a no. We say it is what? It is a no. All right. Let us proceed. Next question here says what? Yes, question 9 now. They say here that the graph below shows how the induced current in the generator varies with the time. We have induced current here. This is time in seconds. Okay, they say here, name the type of generator, choose from AC or DC. Now this one here, guys, it is from a DC generator. It's from what? From a DC generator. Why that AC, with our AC, it's always like this one here, ne? Look here. Now for AC, it would come like this, ne? Maximum, minimum like this. Okay, that's for the AC. But now in here, we have like this, ne? So this one, this is DC. Then they say state, the energy while it is in operation, change from what? From mechanical energy to what? To electrical energy. From mechanical energy to what? To electrical energy. Okay. And then they say here that also give a reason why this generator is not suitable for the transmission of electricity over long distances. Now this one, because it's a DC, and we know that here we must use transformers. Transformers don't use DC current, né? So we say it's gonna be too much energy loss, né? So here, because transformers, they don't use what? They don't use DC current. They don't use what? Don't use this kind of current. They can't use it. They can't use this one here. They can't use DC. Okay, that's why we can't be able to do what? To transmit it over long distances. Then they say calculate the frequency at which the coil rotates in the generator. Now from here to here, this is our complete revolution. Ne? This one up to here, and this time is what? 0,02, and that's our which that's what we call what? And so our frequency f equals to 1 over t. Okay, 1 over periodic time t. So it's gonna be divided for me there. 1 divided by what? By 0,02. What do you get by 0,02? What does it give us here? Calculator here. 1 divided by 0.02, it gives us here 50 Hz, okay? Frequency is 50 what? 50 Hz, okay? 50 Hz. And then next year they said that calculate the root mean square current divided by this generator. Or define, first of all, define the term root mean square current. I've always told you to get your definitions right, okay? Now listen carefully. The root mean square current, how do you define it? We say that is the alternating current that dissipates the same amount of energy as an equivalent DC current. I repeat, root mean square current is the alternating current that dissipates the same amount of energy as an equivalent DC current. Let us proceed, guys. I told you now. Root mean square current. How to calculate it? We have the maximum here. This is a maximum current here. So to get our IRMS, the root mean square current, what do we divide? We divide the I maximum, okay, by root what? By root 2, okay? So divide by root 2 here. What do you get now, calculators? I'm gonna say this is 1,1,2, okay? Divided by root what? By root 2. What do you get, calculators, there? What do you get there? 1,2 divided by root 2, 0,85. So this is 0,85 here, 0,85, 0,85 amperes. That is our root mean square current. Then they say here that 9.7, the graph below shows how the induced current varies with time after a change was made to the operation of the generator. What is current here? They say fully describe the change. Fully do what? Describe the change that was made. They say that the graph below shows how the induced current varies with the time after the change was made to the operation of the generator. They say fully describe the change. If you look at what we have here, now how many are they here? This is one complete cycle. This is one half, the other half. Ne? What about now here? This is one, then two. These were two cycles, ne? Meaning what now? You see they're only getting what? And also the current has been reduced from what? From 1,2, 0,6, ne? So for this change to happen, what did they change? It means that the speed of rotation was what? Was divided by 2. It means what? The speed of rotation, okay, the speed was what? Was divided by 2. Was divided by 2. All was half. That's why the speed of the current is decreases by 2. What cycle? Now it's only one cycle other than 2. So the speed was halved. Let us proceed. Next question. Yes, question 10. Define the term photoelectric effect. Define the term photoelectric effect. It is the process whereby electrons ejected from a metal surface when light of a suitable frequency is incident on that surface. I repeat, the photoelectric effect is the process whereby electrons are ejected from the metal surface when light of a suitable frequency is incident on that surface. They say that red light, blue light, and green light are shown simultaneously on a sheet of potassium, as shown in the diagram below. Each color of the light consists of what? A single frequency. We have got the two maximum kinetic energies of the digital electrons are possible, namely 6,96 x to negative 20 joules and then 2,65 x to negative 20 joules. Each ejected electron has only one of these maximum kinetic energies. You've got the red light, blue light, and green light here. It's potassium sheet here. I repeat, red light, blue light, and green light are shown simultaneously on a sheet of potassium as shown in the diagram below, each color of light consists of a single frequency. The two maximum kinetic energies of ejected electrons are possible, namely 6,960 times 10 power negative 20 joules, and then 2,65 10 power negative 20 joules. Each ejected electron has only one of these maximum kinetic energies. So you have got a red light, blue light, and green light. So you say here that which color of the light is responsible for the ejecting electrons that have a maximum kinetic energy of what? Equal to 2,65 10 power negative 20 joules. Okay, so they say which of these colors um gave electrons with this kinetic energy. So here, what do we need to know? Now, guys, don't forget your theory. Don't forget your theory. You know that the blue end and the red end is for the red shift, which connotes the lower frequency. Which connotes what? Lower frequency altogether. And then the blue end, it has the blue shift, which connotes what? The higher frequency. Okay. In other words, on the spectrum, the blue end has the high frequency. So now in here we have red, we have blue, and then green. Now in our spectrum, the green has a lower frequency than red, and red has got a lower frequency than blue light. So if you check what we have here, because we have the 2,65 times 10 to the power negative 20 joules, which is lower than the 6,960 times 10 to the power negative 20 joules, means that the 6,96, because it is bigger than this one here, that must have been for the what? For the blue light. So this one is for the blue light, okay? And then this one, which is smaller, this one here is for the red what? Red light. And then the green one, dololo, because the frequency is too smaller than what? The threshold frequency. That's why it will not give out any photoelectrons. So here the answer is what? Is red light. Okay. They say explain your answer because only the red and the blue lights can give what? Photoelectrons. And we know that the red light has got what? A lower frequency than that of the blue light, and hence it will give us those of lower energy, which is 2,65 x power negative 20, other than what? The high energy from the blue, which is 6,960, 10 power negative 20 joules. Okay, so next question here. The electrons with a maximum kinetic energy of 2,65 10 power negative 20 joules are ejected by electrode that has a frequency of 5,85 10 power 14 Hz. Is calculate the frequency of light that calculate the frequency. Okay, for the frequency here of light ejected electrons with what? Kinetic energy of what? Of 6,960 10 power negative 20 joules. Okay, so now they say that this kinetic energy here is from light. It has got this frequency here. Now we want to know the frequency which can produce this type of other kinetic energy. So this one here, the first information here, we can use it to get our wave function for this potassium. Okay. When we know this wave function now, that we know the kinetic energy for the other light, then we can know the frequency for that particular blue light. Okay, so now here we know that our energy for the given photon, okay, is given by that energy for the given photon is divided into two, the work function, then plus maximum kinetic energy, plus maximum what? So in here, now here, because they gave us the frequency, which is on here, we note that is h times frequency altogether. Now we don't know the work function, that's what we're looking for in the first case, okay? Then they gave us the what? The EK maximum, okay? So here we can find our what? our wake function. Now Planck's constant is given by what? 6,63, okay, 6,63 times 10 to the power what? Times 10 to the power of negative 34, okay, negative 34. Then they give us the frequency here, which is this one here. They took 5,85, ne? That's 5, what? 5,85, okay, and then times 10 to the power of 14, ne? 10 to the power of 14, are we together? Is equal, actually I'm going to say minus ek because I'm looking for a function, ne? Now this one here is our hf, ne? So minus ek, they gave us this one here, which is 2, what? 2,65, ne? 2,65, 2,65 times 10 power negative 20 joules, okay? Power negative 20 joules. Power negative 20 joules. Power 20, times 10 power negative 20, sorry. Times 10 power times 10 to the power. Okay, so from here now, I'm going to get my wake function W naught. Ne? Okay, calculators, what do you get there? W naught equals to what? Calculators, multiply this one, Planck's constant times 5,85 exponent 14. This is 14 here. And then minus 3. What do you get there? Calculators here, what do you get? Here I'm getting my wake function. My wake, it is 3,61 exponent negative 19 joules, okay? 3,61, 3,61. This is 3,61 times 10 power negative 19 joules. Now that I know the wake function, I can now get to know the frequency of the other blue light now. Ne? Again, by using my E, or you can say HF, all together, equals the wake function, okay? Wake function, then plus now this other what? Kinetic energy, this one here, which they gave us, 6, what? 6,96, 6,96, okay? Times 10 power what? Power negative 20. Power negative 20. Okay, so from here, to get my I'm looking for this frequency, don't forget, okay? So, wake function I know it is the 3, what? 3,61, okay? Times 10 power negative 19, okay? Negative 19. And then plus now, 6, 6,96 here. And then times 10 power what? Power negative 20. Negative 20 here. Then now divided by Planck's constant, which is 6,63. Okay. Times 10 power negative 34. Power negative 34. Okay, so here my frequency equals, calculators, please get me the answer here. What do you get there? Here I'm getting, if I divide it, it gives me here, I'm exponent 14 hz, okay? So this is 6,5 times 10 the power of 14 hz, power 14 hz, power 14 hz. All right, hope we're together, guys. Okay, then next question here says what now? Let's check it out as we conclude this. They say that the intensity of the red light is increased while the intensities of the blue light and the green light remain the same. What effect will this change have on the rate at which electrons are ejected? Choose from increases, decreases, or remain the same. I repeat the question here. They say that the intensity of the red light is increased while the intensities of the blue light and the green light remain the same. They say what effect will this change have on the electrons are what are ejected? Choose from increases, decreases, remains the same. So what do you think here? What do you think here? I said that the intensity of the red light is increased while the intensities of the green light remain the same. They say what effect will this change have on the rate at which electrons are ejected? Choose from increase, decrease, or remain the same. Here the answer is remain the same. The answer is what? Remain the same. Okay, we talked about the change in the frequency, the change in the intensities, and I hope you guys remember this, okay? Then lastly here, they said that some of the atoms of hot gas made up of single element are in an excited state. The spectrum formed by the hot gas is observed on a screen in a darkened room. The spectrum consists of specific colored lines on a black background. Name the type of spectrum formed. Now that one is called the line emission spectrum. We talked about it as well. It's called what? Line emission spectrum. They say here, explain the presence of the colored lines in the spectrum. Okay. Explain what? The presence of the colored lines in the spectrum. Now here, it's because the colored lines represent the frequencies of the emitted photons when atoms move to a lower energy level. I repeat, the colored lines represent the frequencies altogether of the emitted photons when atoms of what? When atoms move to a lower energy level. Alright guys, thank you so much for watching. See you again. I wish you the best tomorrow. Let's do your physics. Bye bye.